Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about stars. We have already looked into exoplanets, we looked into habitable planets. Let's look at the core of it. So basically what we are talking about here, we are talking about something that is made out of gas clouds. And these gas clouds are huge, as in light years across, sometimes multiple light years across. And once you have gas cloud, the probability of all of the atoms in the gas cloud to be equally distributed would be zero. There would be like one clump here, one clump there. So whenever that happens, gravity starts to take hold. Basically it will slowly starts to collapse on unbalance. Basically it will try to equalize and end up collapsing into each other, and over time you will have a ball of plasma, and that plasma would be powered by fusion, because again enough of the material falls into the central point, the central location. Basically the core of that collapsed ball will have enough high temperature, enough pressure to ignite fusion, and it creates its own light. Most of the light you see in the night sky is generally comes from this process itself, and this is the primary energy source. Because if you take a big bang, you remove that from the equation, where else all the other energy comes from? Generally 99.99% of the time it's coming from a star, one way or the another. If you are seeing a volcano erupting, there is a very good chance star directly had something to do with it. If you are seeing clouds moving one place to another, a star has something to do with it. So primary energy source everywhere is generally a star. Now this is a big astronomical object, because if I say moon, you can inherently picture moon because again you can see it. But what is the size difference between moon and earth? It's big, but again it's in the kind of same ballpark. Basically both would be measured in kilogram, let's just put it that way. But what about measuring earth versus sun? That would be like measuring something that is in like kilobytes versus petabytes. So there is a huge size difference between a star and a planet, so to say. So it's on a different ball game. Anything that is generally bigger than this would be like cluster object, basically a stellar system or Milky Way or galaxy, something like that. Basically as a single unit, this is the biggest as you're gonna get, unless you count gas cloud itself. So how the heck does things work? Again, it requires energy. So energy comes from the delicate balance between fusion and gravity. Now I am saying delicate balance between imagine gravity was not there, again the core will not get hot enough for fusion to occur. So that's why it's a delicate balance. Basically gravity starts collapsing at the ignition point. The core becomes hot enough to fuse. Fusion puts outward pressure. So there is an equilibrium. Basically inside is pushing out, outside is trying to crush it in, and there is a balance between that. Now most of the stars 90% of the time spend in this perfect equilibrium. So if you see the star size, it will not change for 90% of its life unless it starts to run out of fuel or it's just being birthed into existence. So once this equilibrium reached, it will remain there for a very long time. So what is actually happening? Now you have to understand one core aspect. Gravity never shuts off. Fuel may run out, but the gravity will not shut off. Once it's a universal principle, so gravity will not shut off. So what generally stars do, they take hydrogen, the primitive element, and they collapse it into helium. Now what happens once you run out of hydrogen? You take helium and you still collapse it into carbon and oxygen. Generally this process is classified as helium flashing, and its technical name would be triple alpha process. So basically you take heavier elements, collapse some more helium into it, you create carbon, you take more helium into it and you get oxygen out of it, and that's how you keep running the fuel. Basically you are getting extra mileage out of that. So it's not like once you run out of hydrogen, game over. It's not. However, the moment you run out of hydrogen, you reach into what we could be classified as oscillation. Basically it will start going like this because equilibrium is no longer there. So once you reach into helium phase, if our sun reaches that, it will become a red giant because the energy output will be completely different. So what happens once you reach to oxygen level? Again, you will run out of oxygen at some point. You will start to collapse that into neon, and then you will start, same process will happen. You will start to run out of that also. Then you will collapse it into silicon. What happens after that? You reach iron. Now this is the end game. Once you have created basically the moment you reach in periodic table number 26, game over. You cannot fuse any further than that, because any fusion occurrence that will happen after 26 will absorb energy. It will not give you energy that will allow the gravity to form. So basically energy for counter gravity, so to say. So that's the end game. So a star can live for very long time even if hydrogen is over, because helium is powerful, carbon, oxygen, all of them, they have more than enough power. But the moment you reach iron, game over, the end. And that's at periodic table number 26. And that's why if you start to take a basically elemental graph of the whole universe, you will see everything present in a very large amount before iron. After iron, you will see the percentage drop drastically, simply because creating anything heavier than iron is much more difficult, because again even a star cannot do that. So all these things you have to understand, all of this is controlled by one core factor: mass, gravity. Everything is going around mass. So size matters. Yes, like in this scenario, size absolutely matters. It controls everything, basically from birth to death. Everything is controlled by mass. Now there is a simple rule for this, which is if you are big, as in like really big, as in much bigger than sun, you will have a shorter lifespan. Basically you will live only few million years, and then you will be very bright, as in like immensely bright. Your brightness would be like multiple times more of the sun. So what happens on the other end? Basically that's what happens when you go YOLO big. What happens if you go very small? You will end up living in a very longer life, in hundreds of billions of years, and you will be very dimmer. So basically you would need to like have a very powerful telescope in order to see it. And that will also affect what kind of matter ratio is created once you go boom. Basically how much carbon you will have, how much silicon you will have, how much iron you will have. That all would be controlled, fine-tuned by mass aspect of it. Now, how do we measure it? Because that's the first thing that should come at your mind. These things are not something, oh, I'll go there and measure Mount Everest. It's not like that. So how do we measure it? Well, we utilize parallax. You want to understand parallax? Extend your thumb like this and close one eye after the another. You will see things behind your thumb move left and right. And if you know trigonometry well enough, you can calculate that. And if you have students to teach why the heck they should study trigonometry, you can sell this part, like this will allow them to study basically distance of the stars. Now if you are familiar with geometry, you will understand, hey, this is not doing too much. How the heck I'm gonna affect basically stars that are multiple light years away? Well, you can't. Practically you cannot be far apart on Earth. So what we utilize is Earth orbit itself. So you have to understand, from Earth is centered around sun to Earth, the gap is what we classify as one astronomical unit, aka around 8 light minutes. What happens, you go from August to February, you are talking about 14 light minute apart. You are 14 light minute apart. That's a huge distance. At that point, stars starts to go from wonky left to right, left to right. And utilizing this parallax effect, we can calculate with quite high reliability how far the stars are. And again, we in earlier days we could not have calculated for very very far apart, because again, the further they go, the less the parallax will become. So again, we needed modern instruments to calculate something like 50 million light years and all that. You need better equipment for that. So that's how we calculate the distance up. Basically we utilize Earth's orbit. Once we start having civilization on Mars, we'll have even higher resolution, because again, we'll add few light years on both end. Light years, I'm saying, sorry about that, light minutes on it. So what about the lifespan? Now this is the part which is very difficult to understand, because the numbers are huge, as in ludicrously huge, as in so huge human brain cannot comprehend it. It's like if I say 2 people die, you can understand. If I say 2 million, that your brain will simply reject it. Like there is a filter. Like once the number becomes too huge, your brain is like, I can't handle this. So massive stars, they have very short lifespan. Yeah, short lifespan means millions of years. I'm like, what the hell? And millions of years is so large, even in terms of planets. Like Mount Everest would not be there after millions of years, because again, if you go millions of years in back, you may end up in a scenario where tectonic plates have created something different. So you can understand, millions of years is completely different, and that's the small lifespan. What about the smaller stars? They could go from hundreds of billions of years to thousands of billions of years. That's like ludicrous amount of zero in that. So our sun is in its middle age. Basically all our mathematics suggests that if sun has a 0 to 100 lifespan, it has crossed the 50% mark. So are we in a basically hurry? Well, yeah, we have only 4 billion years left. So you can understand this aspect. It's inherently incomprehensible to human mind. What about the death, the end game? Now death event directly depends on mass. Everything about star depends on mass. So a star can take many number of parts. So even if you take a star catalog and you're like, okay, I'm seeing this star, one star here, another star here, and they are like in the same category, and both of them are about to go boom, would they have same outcome? Not necessarily. A star can take multiple paths, so to say. So massive, what happens when you have something massive? It creates supernova. Now the supernova is such a high energy event. It releases more energy like in that instant compared to like the whole lifespan of the star could be glowing for millions of years. The total energy output will, let's say, 1 gigawatt. One basically supernova in 1 second will create 1 terawatt. So this supernova event creates heavier elements. Basically, if you are familiar with periodic table, you know for a fact there are more heavier things than iron. Where the heck they are coming from? Supernova. And that's why we know for a fact like life could not have originated very early on in Milky Way, basically in this like universe basically, because you have Big Bang. After that, you have to wait for big stars to be formed, and then go to boom supernova, and then they will enrich this universe with heavy elements, basically heavier elements in the periodic table. So that's how it's created. And every time a nuclear reaction is happening, that's the only time you are bypassing the stars requirement. Basically, you burn coal, that's solar energy. You wind power, solar energy. Everything is solar energy except when you go nuclear system, because at nuclear you are utilizing fission wise, not fusion wise. Fusion wise you are utilizing supernova, because if you go fusion route, that's directly utilizing Big Bang. So that's how supernova creates heavy elements. Now that's the core reason. Like if you take iron before it, you will see it everywhere in the universe. The moment you go after iron, it's like very scattered. The core reason for that, stars cannot create it reliably enough. Now remaining, what happens to the core? Like you have to understand, it's a symmetrical thing. Like a star is a sphere, it collapses on itself, so something will remain in the center because it's a uniformal, basically completely symmetric thing. It will remain something in the center. So you will have three options depending on your star's mass. Basically, if you are something like low mass like our sun, you will have white dwarf, powerful but not that big. But what if you are really huge? You can go into neutron star. It would be very dense, but the gravitational impact would be YOLO huge. And what if you are really, really, really crazy big? Then you will go to black hole. So these are generally the three outcomes. Now, neutron star to black hole, they are kind of very close to each other. We can definitely predict whether it's going to be white dwarf or neutron star, but we cannot predict whether it will be black hole or neutron star. The gap between white dwarf and basically white dwarfs are generally very easy to predict, like based on star size. So these are the outcome after death. Now be mindful, stars we have been studying from 1800s. It's subject that we know, like as in thoroughly know and thoroughly studied, and like created so many measurement units out of that. It's on a different level. Like you have to watch like hundreds of hours of video to understand what we understand right now. So this was my small attempt, hopefully to give you enough context so you can understand what the heck people are talking about when they are talking about stars. Hope you liked it, learn from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.